All right, I'm going to be concise today with these notes. Basically, so this is just notes. This isn't really how to do specific problems. The main focus is how to identify different types of chemical reactions, the 5 major types that we talk about in class, and that you're likely to see in like any chemistry class you take. So what I'm going to do is walk through these. These are the slides that you can find directly on the class website. Yeah, I think it's slides 12 through 17, I think, if I had to guess. I think that's what it is. So just know that that's what we're going to be looking at. So what I want to do, I'm going to walk through the 5 types of reactions. I'll explain each type, show you an example. This is not going to get into the specifics of predicting double displacement or single displacement reactions using like the activity series or any of that. That'll be a little bit later in the class. But for right now, all right. Now, synthesis reactions. First thing you'll notice is that there are boxes instead of arrows because my printer is useless. So I'm going to put arrows in here. The boxes are just, pretend the boxes aren't there. So we've got our general reaction. So this is a synthesis reaction. This is the first one. And like I said, I'm going to be fast and concise on this. So we got synthesis. Sometimes this is called not just synthesis. This can be called a combination reaction or sometimes even a composition reaction. I call it synthesis, but then plenty of other people call it combination. It's exactly what it sounds like. It's just when you have two substances. So like you have two things, and they are going to react to produce one thing. So you just have something plus something else. I have no idea why I used X. It should have been a B. And it just makes, so they are there. They combine, they synthesize a new substance. So you have two making one. Or sometimes it's not always two things making one. You could, I suppose, you could have like three things that make one thing. So, that is a possibility too. But the general idea is, two things make one thing. That's the general form. Doesn't matter what it is. All right. So that's synthesis. This is probably the easiest one to spot, I think. Next, we have decomposition, which is basically the opposite of synthesis, which is also very easy to spot. So it is just one thing breaking down into two or more products. You're decomposing, so you have it breaking apart. I don't really know if there's a different name for this. I think it's just decomposition. I've never heard it called something else. So you have decomposition taking place when you have one thing breaking into two or more things. Very simple again. This is a good example. There's plenty of examples, but this is the basic form. So, and when I say this, and just to be clear, I'm sort of viewing the arrow for all these reactions, for synthesis or whatever. The arrow is kind of the dividing line that I'm looking at when I say you have one thing breaking into two things, or two things making one thing. All right, so you have one reactant makes two products in a decomposition reaction. Simple as that. Now, single displacement reactions. This is where it starts to get a little more confusing, a little more challenging. But once you get the hang of this and once you just do some of these practice ones, it won't be a problem at all. Basic idea for a single displacement reaction is this. So in this case, you'll notice that you have a single element plus a compound. All right, that's going to react. It's going to produce a compound plus another single element. That's why we call it a single replacement. Sometimes this is called, or I call it single displacement. Sometimes it is called a single replacement reaction. I don't really know which terminology. I'll use displacement, so that's the one you're going to have to know. Now, to do this, the basic idea is, like I said, it's one element reacts with a compound, produces one element in a compound. Now, it's a little more complex than that in reality, and like sometimes the reactions happen, sometimes they don't. But basic, and also remember that it doesn't matter which thing's first. Like the compound could be first, the single element could be second. It doesn't matter. The plus, it doesn't matter which thing's first or second there. It just matters which side of the arrow it's on. Now, this we'll get into a little more specifics. So, imagine in this case that that you have, you've got your magnesium, you got your hydrochloric acid. They're going to react, and in this case, what switches with what makes a difference. So, let's look at our compound. So magnesium, if you look it up on your ion chart or your periodic table, so magnesium, if you look it up on your ion chart or periodic table, I just pause, so I'm unpausing. It has a charge of +2. Magnesium is +2. All right, that matters for right now. Next, I'm just focusing. Next, you keep going and you look, and first this coefficient, that doesn't really affect what type of reaction, so don't worry about the coefficients. They don't affect the type of reaction at all. Next, we've got hydrogen. Hydrogen is a +1 charge. Chlorine is a -1 charge. Now, what we care about in this case, we care about what has like charges, similar charges. So you look at this and you're like, all right, magnesium is a positive charge. Hydrogen is a positive charge. We don't care that it's +2, +1. We just care that they're both positive. So what's going to happen between those two during this reaction? They're going to switch or trade places, whatever you want to call it. They're not going to combine. When I draw that line, sometimes people think they're going to combine. No, they're going to switch places. They're going to trade places. So the magnesium will take the place of the hydrogen, and the hydrogen will just take the place of magnesium. It's basically like, imagine you got hydrogen and chlorine. They're dancing. They're having like a nice little dance or whatever, and magnesium's like, hey, can I cut in, man? And then hydrogen's like, okay, and then it leaves. Though that doesn't always take place. Sometimes it doesn't happen, but we'll talk about that. That'll be like the next lesson thing. But in general, that's the deal. So they switch, and then you look, you see hydrogen now is by itself. It was over here. Now it was over here in the compound. Now it's not. It's by itself. Magnesium was an individual by itself. Now it is in a compound. That is a single displacement reaction when you have a single element that trades places. All right, and they do it based on like charge. Now, double displacement reactions. These are definitely, I think, the most challenging, or at least they can be. So I want to make sure we get into that a little bit. We're almost done, though, actually. Basic idea, double displacement reactions are almost exactly the same as single displacement reactions. The only difference is that instead of having a single element, you have two compounds. So you have two compounds, they react to produce two compounds. There are no single elements in a double displacement reaction. The basic idea, though, is the same in terms of like charge switches with like charge. So let's say that you have, in this case, you have potassium, it's a +1, iodine, -1. Lead, in this case, would be, so nitrate is -1. You have two of them, so lead would be a +2. So in this case, the like charges, so you want to make a note that like charges switch. All right, like charges are they're going to trade places. Now, when they'll, and that means, so like, or we'll say same, whatever. So in this case, it doesn't make a difference. You can pick the positives or the negatives. It doesn't matter because you get the same result either way. So I always just do the first two. So we're going to say that these two are going to switch. They're going to trade places. So that means that, K, potassium, and lead are going to trade. And then look, so now all of a sudden, lead is bonded to the iodine, whereas here, the potassium was bonded to the iodine. And then all of a sudden, potassium is now bonded to nitrate, whereas before, lead was bonded to nitrate. Now you then have to go write the formulas correctly, and you got to balance it and all that. But the general idea, the general form, is intended to be, it's intended to be pretty simple. Okay, sorry, somebody walked by and yelled, and I was like, no, I'm recording a video. I don't want that. Okay, so you're going to switch the like charges, but again, you could have done the negatives. It would have given you the exact same result because remember, it doesn't matter if you wrote down this. If you wrote down that instead of this, it's the same thing. It doesn't matter which one's first and which one's second. It's all the same. All right, so that's a double displacement. Two compounds react with two compounds, or they react to produce two more compounds. Double displacement. Okay, these are the longest ones. They look the longest. The big difference, again, single is a single element. Double is two compounds. And last but not least, combustion reaction. This one is actually pretty simple. All right, so simple combustion reaction. Combustion is another term for fire. Fire is cool. We like burning things in chemistry. And we will burn things in chemistry when you return. I promise. So, general idea is that, you have a hydrocarbon combining with oxygen to produce fire, pretty much. Now, the way this works, you're going to combine, like, the products, or I should say, let's just begin with the reactants. The reactants, the stuff you begin with in a combustion reaction. Two things always. One of them will always be a hydrocarbon. That means it'll always be C and O, or pardon me, it'll always be C and H, and there'll always be like a C and an H with some subscripts there. It doesn't really matter what they are. And like every once in a while there might be an oxygen there. But generally it's going to be a C and an H. All right. And I mean, we're talking like C2, H4, like whatever, any of that. Like that's an acceptable example. It doesn't matter. All right. Now, the second reactant will always be oxygen, because what does fire need to burn? Oxygen. Without oxygen, there is no combustion, there is no fire, it doesn't happen. So this second thing, it must always be oxygen. Though you could write, so like for example, so let's say C2H4 plus O2 gives us some stuff. Or you could write O2 plus C2H4. It's the same stuff. Like, so just to show you, it's the same result. It doesn't matter. Understand that the order of the reactants or products doesn't matter as long as they're on the right side of the arrow. Correct side of the arrow, I should say. So you do that, and then the products of all combustion reactions. This is the nice thing. Well, it's nice in that it's really simple to identify and predict, like to predict what you're going to make, but then balancing these suckers, balancing combustion reactions is very frustrating sometimes. It can be hard. So, as you already know. So you can do this, and you'll get your C2H4 plus O2, and what you're going to see, the products are always carbon dioxide and H2O. As you can see, H2O, CO2. Doesn't matter which way you write it. Doesn't matter. There you go. Then what you would have to do is go back and balance the reaction to make it right, which we're not going to talk about balancing right now. But that's just the general form of a combustion reaction. So these should be the easiest, honestly, to identify, because you'll pretty much see this. You'll see some C with some number and H with a number. Those are variables. Plus O2 will produce CO2 and H2O. Always. That's what it will produce. Is it? So if you see that, you know it's a combustion reaction. So those are the 5 types of reactions. There you go.